Welcome to the third video of the refrigeration fundamentals. The final video will explore the pressure enthalpy diagram. A refrigeration system transfers heat. Heat will flow from points of higher temperature to points of lower temperature. In the evaporator, the heat transfer is known as heat of absorption. Heat is absorbed into the refrigerant because the return air temperature is greater than the refrigerant temperature. During this process, the temperature of the air will be lowered. In the condenser, the heat transfer is known as heat of rejection. Heat is rejected from the refrigerant and into the outside air because the outside air temperature is lower than the refrigerant temperature. Therefore, the comfort cooling refrigeration cycle absorbs heat from the inside and rejects the heat to the outside. The pressure enthalpy diagram is a tool for refrigeration engineers and designers, but it is also a useful tool for illustrating the refrigeration cycle. The pressure enthalpy diagram shown is a version that has information missing. The objective is to gain a general understanding of how the pressure enthalpy diagram can help technicians analyze the refrigeration cycle and how it can be used to improve refrigeration diagnostics. To begin, the horizontal lines are absolute pressure. The vertical lines are enthalpy. The dotted lines are the temperature of the refrigerant. The shark fin or thumbprint curve is the saturation curve. To the left of the curve is liquid. To the right of the curve is vapor. And within the curve is saturated refrigerant. Saturated refrigerant is the mixture of vapor and liquid. The temperature will remain constant when the heat is rejected or absorbed. The data from the instruments can be plotted onto the curve, and then the refrigeration cycle can be drawn. Begin by drawing a line for the saturated temperatures. Mark the refrigerant temperatures at the compressor inlet and outlet. Mark the inlet temperature of the TXV. Finally, connect the lines. The compressor increases the pressure, temperature, and enthalpy. The refrigerant has the highest energy at the compressor outlet. The condenser coil desuperheats the refrigerant until it reaches the saturated condensing temperature. This saturated refrigerant maintains constant temperature. Once all the vapor has condensed into 100% liquid, the refrigerant temperature will be lower than the saturated condensing temperature. This is known as subcooling. The metering device reduces the pressure and temperature without a change in enthalpy. The saturated refrigerant temperature remains constant. Once all the liquid has boiled into 100% vapor, the refrigerant temperature will be higher than the saturated evaporator temperature. This is known as the superheat, and the cycle repeats itself. The information from the pressure enthalpy diagram can be overlaid onto our refrigeration cycle and then draw the saturation curve. Since refrigerant is abstract and cannot be seen, technicians must rely on field instruments to verify system efficiency. The goal of this video is to give a visual representation of the refrigerant as it goes through the refrigeration cycle. The data on the low pressure side of the circuit shows the evaporator pressure equals 125 psi, with a saturated suction temperature equal to 42 degrees. Beginning at the evaporator saturation curve, when the refrigerant crosses the saturation curve, it will have changed state to 100% vapor, and any heat absorbed will increase the refrigerant temperature. This is known as superheat, which is defined as the temperature above the saturation temperature or the boiling point. As the refrigerant travels further past the saturation curve, the refrigerant continues to absorb heat from the air. The temperature at the TXV bulb is 52 degrees. So, the refrigerant temperature is 10 degrees above the saturated temperature, or 10 degrees of superheat. This superheat is referred to as the evaporator superheat. Additional heat is absorbed as the refrigerant travels through the suction line towards the compressor. The refrigerant temperature at the compressor is 57 degrees. So the refrigerant temperature is 15 degrees above the saturation temperature, or 15 degrees of superheat. This superheat is referred to as the total superheat. The compressor compresses the low pressure superheated vapor into a high pressure superheated vapor. The heat of compression will add heat to the refrigerant as it discharges from the compressor, increasing the superheat. The data on the high pressure side of the circuit shows the condenser pressure equals 300 psi, with a saturated condensing temperature equal to 96 degrees. The temperature of the refrigerant at the compressor equals 141 degrees. So the refrigerant temperature is 45 degrees above the saturation temperature, or 45 degrees of superheat. As the refrigerant travels through the discharge gas line into the circuits of the condenser, the first function of the condenser coil is to de-superheat the refrigerant. Just before the refrigerant crosses a saturation curve, the refrigerant will be above the saturated condensing temperature. When the refrigerant crosses the saturation curve, the temperature of the saturated refrigerant will be 96 degrees. As the refrigerant travels through the condenser coil, rejecting more heat, the vapor condenses into a liquid and does so without a change in refrigerant temperature. As the refrigerant travels further through the condenser coil, just before it crosses the saturation curve, the refrigerant temperature will be 96 degrees and mostly liquid. Once the refrigerant crosses the saturation curve, the saturated refrigerant has changed into 100% liquid and begins to subcool. Subcooling is defined as a temperature below the saturation temperature or boiling point. As the refrigerant travels further through the condenser coil, the refrigerant continues to reject heat and subcools the refrigerant even more. The temperature of the refrigerant leaving the condenser is 86 degrees, so the refrigerant temperature is 10 degrees below the saturated temperature, or 10 degrees of subcooling. The subcooled refrigerant travels through the liquid line, through the filter dryer, and into the TXV. The TXV reduces the pressure of the refrigerant, meters the amount of refrigerant into the evaporator. The change in pressure converts a small amount of liquid into vapor. The refrigerant, when leaving the TXV, is a low pressure, saturated refrigerant. The refrigerant travels from the TXV through the distributor tubes and into the evaporator. As the refrigerant absorbs additional heat, the temperature remains the same while in the saturated phase. Once a refrigerant crosses a saturation curve, it becomes 100% vapor, and any heat added to the vapor will superheat the vapor. Then the cycle repeats itself.